Hello and welcome back. This is Chapter 4, Video 1, where we'll be introducing the natural deduction system for our language S. That system is called SD. Truth tables and truth trees provided ways for testing for validity and other logical properties. This is a third such way, but it differs from the other two in that we will not be looking at truth values of the relevant formulas. Instead, we're going to develop a symbolic system that in some ways mimics the way we might naturally deduce conclusions from premises. For example, consider the following argument. If Carol drives, Ann will go to the fair. Carol will drive if Bob goes and pays for gas. Bob will pay for gas if Ann promises to pay him back. If Bob lets Ann ride shotgun, she will promise to pay him back. Bob in fact goes to the fair and lets Ann ride shotgun. So the conclusion is Ann goes to the fair. Now how do we determine if this is valid or not? We could do a truth table, but it'd be an awfully long one. We could do a truth tree. Neither of those methods actually tracks how you might in fact determine the validity of this argument in your head. Consider how we might actually deduce this conclusion from the premises. Here are the original 5 premises. If we can follow a train of reasoning from these 5 premises all the way to the conclusion, where each step in the reasoning is itself a mini valid argument, then we'll know that we validly deduce the conclusion. So let's see if we can do that. Here's premise 5. Bob goes to the fair and lets Ann ride shotgun. So it's obvious that Bob lets Ann ride shotgun. That just comes from premise 5 and a valid inference. Every conjunction implies each of its conjuncts. Next, look at what we have in premise 4 and premise 6. 4 tells us that if Bob lets Ann ride shotgun, then she will promise to pay him back, and 6 tells us that Bob does let Ann ride shotgun. Those two together imply that Ann promises to pay Bob back, and we can indicate right here that 7 comes from 4 and 6. So with 4 and 6 together and a mini valid argument, we get 7. Now if we pay attention to 7 and 3, 3 tells us Bob will pay for gas if Ann promises to pay him back, and 7 tells us that Ann promises to pay him back. So those two together give us that Bob pays for gas. Now look again at premise 5. The other half of that is that Bob goes to the fair. So 5 all by itself implies that Bob goes to the fair. Now if we take 8 and 9 and put them together into a conjunction, we get 10. Bob goes and pays for gas. But if you look at what 2 says, Carol will drive if Bob goes and pays for gas, and 10 tells us that Bob goes and pays for gas, then those two together give us this sub-conclusion. Carol drives from 2 and 10. Finally, if we look at the original premise 1, if Carol drives, Ann will go to the fair, and our sub-conclusion 11, that Carol drives, then we get our ultimate conclusion that Ann goes to the fair. That comes immediately from 1 and 11 and was our original conclusion. So what we've shown is that from the original 5 premises, through various steps of valid argumentation, we can draw a series of sub-conclusions which ultimately leads to the overall conclusion. Since each step is valid, the whole argument is valid. What we're going to develop and introduce in this video is a symbolic means for doing exactly what we've just done. We'll have a certain set of rules for drawing conclusions from existing premises, which can then be reapplied to the sub-conclusions in an effort to draw the ultimate goal formula or conclusion of the deduction. In fact, if you look at this slide, you see the original argument on the right-hand side, and you see a derivation, which is our name for these symbolic deductions. You see a derivation on the left. If you'll note, each of the premises on the left is a symbolization of the premises on the right, and each step below that horizontal line is a symbolization of the steps over here. Just like in the English version, where we've listed a justification for each of the sub-conclusions and the ultimate conclusion, in our symbolic derivation we also list line numbers as justifications and special abbreviations of rule names for the rule of inference that allowed us to draw that conclusion. I'm not going to worry about the exact meaning of these right now. That's what we'll talk about in the remainder of this and the next video. But you can see the pattern is 5 primary assumptions or premises, the 5 original premises, and then a series of steps, each of which is a valid inference of some sort, ultimately leading to the original desired conclusion. And the way you'll see derivations are set up is every derivation will have this vertical line, which is called a scope line. Some derivations will have more than one scope line. We'll get to that in due time. And most derivations will have a set of primary assumptions. That's sort of your starting position, or the material with which you'll be able to work. And then there'll be a goal formula, usually not that simple. A goal formula, which is your ultimate conclusion. And the primary assumptions are set off from the work you do in the derivation by this horizontal line. And then you'll have various formulas listed next to the scope line with their justification on the right-hand side there. Now all I want you to understand from this really is the parallel between what we're doing over here symbolically and what we've done over here in English. The remainder of this video will introduce you to the various rules for derivations. Now, as I mentioned, we're going to have a system of rules for doing these derivations. In fact, there will be 11 derivation rules. We'll have 2 rules for each connective. An introduction rule, which allows us to generate sentences including that particular connective, and an elimination rule, which allows us to deal with, take apart, or eliminate sentences containing that particular connective. And since there are 5 connectives, we get 10 rules. And then there is an 11th rule called reiteration, which allows us to rewrite any line that we already have at some later point in the derivation. In fact, that's the first rule we'll introduce. So here is the reiteration rule, which is the simplest of the 11 rules. This R is the abbreviation for the reiteration rule. And you'll see in the schematic here, what you have is a scope line and some line of your derivation. It doesn't matter where or when you are in this derivation. We'll call it line I. If you have some sentence P, and remember as a meta variable that can be any sentence, then what you're allowed to do, the result of applying the rule, is just reiterating or repeating that line somewhere else in your derivation. And your citation to justify that step would be to cite the original line and write an R for the reiteration rule. Now this rule may seem sort of silly because all it does is allow you to repeat yourself, but as we'll see down the line, it has certain specific uses. For now, let's just illustrate how it goes. So you might be given a derivation with a couple of primary assumptions, perhaps like this. Now I won't specify any particular goal for this derivation. We're just going to play around with the reiteration rule, so there's no need to specify a goal. All this allows us to do is to say, take line 2 and write it again on line 3. And our justification over on the right-hand side would be line 2, reiteration. We could, of course, take line 1 and reiterate it. And keep in mind, we cannot change the line when we're applying this rule. What we rewrite has to be exactly the same as it appeared in the prior line. In fact, we could write a line like this, F arrow E, and that could have either come from line 2 or line 3. So it doesn't actually matter what we put in as the justification. We could either write 2 reiteration, or we could write 3 reiteration. Now, as you can see, this doesn't really take you anywhere, just moving lines further down in the derivation. We could do it to our heart's content, but it quickly gets boring. But that's the basic idea behind reiteration, and as I said, when we get further along in derivations, there'll be a more interesting use for this. Now, 2 much more interesting rules are conjunction introduction and conjunction elimination. You see, we abbreviate conjunction introduction with the wedge for conjunction and an I for introduction, and similarly a wedge and an E for elimination. Now, focus on conjunction introduction on top there. What this is telling you is if you have 2 lines somewhere in your derivation, and on one line we've got some formula, any formula P, and some possibly but not necessarily distinct formula Q, then we can take those 2 pieces and put them together in a conjunction. And the justification will be to cite the line numbers of the 2 components and then the rule name conjunction introduction. We'll see an example of how this works in just a second. Focus on the lower rule, conjunction elimination. This tells you that if on some line of your derivation you have a sentence with conjunction as the main connective, then you can either derive the left conjunct, citing the original conjunction and conjunction elimination, or you can derive the right conjunct, again citing the original line number and conjunction elimination. The rationale behind these 2 rules is, for conjunction introduction, is that if we know that P and that Q, then of course we know that both P and Q. That is to say, a conjunction follows from 2 component formulas. Similarly, if we know that P and Q, then we also independently know that P and independently know that Q. So let's see these in action. Again, we'll do a derivation where we don't specify a particular goal, but we just play around with the formulas that we've got. So let's see, not A and D, C and B and E as our primary formulas, primary assumptions, lines 1 and 2. Now, if you take a look, both 1 and 2 are conjunctions, so we could take them apart if we want to. We could take the right conjunct from line 1 by conjunction or and elimination. So what we've done here is taken this piece, brought it down here since that's a conjunction, and our justification is conjunction elimination. Now, of course, we can equally as well take this piece, bring it down here, and we'll cite the same rule. So let's do that. We take the left conjunct, not A, and the negation sign does have to come along with that because it's part of the conjunction in line 1. And again, the justification will be line 1, conjunction elimination. Now, similarly, we could take the 2 pieces of line 2 and break them apart. what we essentially have there is another conjunction, where C is in the position of the meta P, and the whole sequence B and E is the meta Q. So if we break those up, we will get, let's take the C first. It doesn't matter which side you take first, or even whether you take both sides. C comes from 2 and elimination, and then B and E comes from 2 and elimination. Now what we could do is make some new conjunctions. So take line 3 and let's say line 6. We can put those two together into a conjunction of their own. D and B and E. We have to put the B and E in parentheses to show that they're a unit, and the justification there will be 3, 6, conjunction introduction. So D is playing the role of P here, and B and E is playing the role of Q, and we're putting them each together into a conjunction, just like the rule allows us to do. Now, one of the things that's explained in the book is that the order of the input formulas doesn't actually matter. It appears here that P comes first and winds up on the left, whereas Q comes second and winds up on the right. But it is not the case that the formula that appears first must go on the left, and the formula that appears second must go on the right. In fact, we could just as easily have written the following: B and E coming from line 6, and D coming from line 3. Now I prefer the justification be written in numerical order, 3, 6, and introduction, but really that doesn't matter that much. You could write 6, 3, and introduction. As long as you have both the relevant lines listed there and the appropriate rule name, you're fine. So there are a few examples of and introduction and elimination. Now let's back this derivation up a bit and talk about some things to be aware of. Now, suppose I specified a goal for this derivation, and I want to get to B and D. Obviously, we can do just as we did earlier and get the D from line 1 by and elimination. But can we do the following? I see that I've got a B here and it's part of a conjunction. Can I do the following? B from 2 by and elimination. This actually turns out to be an error. If we're going to apply conjunction elimination to the formula in line 2, it has to be applied to this conjunction, which means the two derivable pieces are the C and the B and E. That is, when applying conjunction elimination to line 2, the only two results we could have are the C or the B and E together. That means that we can't get B in one step from line 2. Rather, we have to take 2 steps to get to it. So instead of trying to get the B straight out of line 2, we can get B and E from 2 and elimination. And since this happens to be a conjunction as well, we can apply a separate step of conjunction elimination to line 4 and get the B from line 4. Now we have our D in line 3 and our B in line 5, and remember we wanted to get their conjunction as our goal, so all we need to do is apply conjunction introduction to 3 and 5, which will give us B and D. And now we've reached the goal of our derivation. So remember, even if every connective in this formula is a conjunction, we can't reach inside of those parentheses to get the b straight out. We have to first break up into at least one of these two pieces, as we did here, and then that can be broken up into its subcomponent. Another way of putting this point is that these derivation rules have to work on the main connective of the line you're applying them to. One of the things that's nice about conjunction introduction and conjunction elimination is that they're very intuitive and straightforward. Anytime that you have two pieces, you can put them together into a conjunction in whichever order you require that conjunction. And anytime you have a conjunction, you can pull it apart to get one or both of its component pieces. So that's the basic idea behind derivations and the first three rules. In the next video, we'll introduce more rules.